If you ask a cybersecurity engineer how to secure artificial intelligence, 90% of them will point to one specific threat: prompt injection. The industry is hyper-focused on the idea that attackers will compromise models by typing something like, "ignore previous instructions." But a basic chat window blocking a bad prompt is a localized, contained application. Enterprise AI doesn't look like this. It is an intricately orchestrated ecosystem. Look closely at this architecture map. A production system is built on autonomous agents, vector databases, long-term memory clusters, API orchestration layers, and external enterprise tools. The large language model itself is not the perimeter. It is merely the computation engine sitting at the center of this massive web. To make an LLM useful, organizations have to connect it to external data and internal infrastructure. Every single connection added creates a new, specific entry point for an attacker. Securing the prompt provides very little protection if the architecture surrounding it is overprivileged and openly exposed. To map how attackers actually break in, we have to start at the outermost edge of the system. This diagram highlights the user-facing entry points, the front end and the API gateway. These outer layers face web exploits like cross-site scripting, amplifying damage in AI. An attacker doesn't need to hack the server. A malicious browser extension silently intercepts data between front-end and gateway, extracting an active authentication token directly from the stream. Stealing a service account key grants the attacker the same administrative privileges assigned to the AI agent. Defending this edge requires security controls, strict OAuth implementations, stringent content security policies, and rate limiting to throttle extraction. If authentication fails, the attacker bypasses the LLM's behavioral safeguards by impersonating a trusted internal administrator. Moving deeper into the system, past the gateway, we reach the routing center. This is where the orchestration layer and the specialized agents operate. Agents make autonomous decisions. The orchestration node expands into a logic tree handling tool selection. A router chooses safe chat or tool execution. Attackers can hijack this workflow. A crafted payload forces the orchestrator to ignore policy, rerouting logic into an execute SQL toolpath. A hijacked orchestrator can trigger infinite agent loops or authorize database dumps. Without strict permission checks built directly into the orchestration layer, the agent executes the hijacked routing logic, even if the underlying LLM would have flagged the intent as malicious. Beyond execution, AI systems need context. They access enterprise knowledge through a mechanism called Retrieval Augmented Generation, or RAG. This diagram shows the baseline mechanics of RAG. A clean PDF document passes through an embedding model, transforming the text into a complex matrix of numerical vectors. Those vectors are stored in the vector database node, allowing the AI to search them. This ingestion creates a vulnerability, embedding poisoning. An attacker uploads a seemingly normal document containing secret malicious instructions, like revealing administrative passwords. The corrupted document is embedded, and its resulting vector matrix hides silently inside the larger database of clean vectors. The threat is latent. That payload can sit in the database for months until an innocent user executes a search query that retrieves that specific poisoned vector. Preventing this requires document validation before embedding, metadata filtering during retrieval, and absolute tenant isolation within the database itself. A single compromised document can corrupt the context window for any future interaction that retrieves its vector. The final step of the AI pipeline is execution. This is how the system reaches back out into the real world to perform tasks. The Model Context Protocol, or MCP, is a universal standardization layer. It allows AI models to securely plug directly into external enterprise tools. This integration model introduces supply chain vulnerabilities. A malicious MCP server can spoof an official integration, pretending to be an internal GitHub server to intercept and exfiltrate proprietary source code. And consider what we are plugging these agents into. They access privileged environments, like AWS management consoles, complex Kubernetes clusters, internal company Slack channels, and raw shell environments. Look at this execution flow. An LLM node attempts to execute a shell command to delete temporary files. But the agent misinterprets the syntax, flashes a recursive delete command, and wipes the surrounding infrastructure offline. These scenarios demand architectural defenses. Enforcing the principle of least privilege and application sandboxing are mandatory for AI tools. Any tool that has the capability to mutate data or alter infrastructure must be secured behind mandatory, human-in-the-loop approval gates. External tools act as the physical hands of the AI. If an attacker controls the execution environment, the safety of the model itself is no longer the final word on security. We also have to account for the persistent components of the architecture: conversational memory and external API state. This introduces the threat of memory poisoning. By instructing the system to always reveal internal documents, an attacker permanently manipulates the memory node. Later, a completely separate clean user pathway connects to this node and is instantly infected by that retained instruction. Agents also inadvertently expose standard API vulnerabilities. Unrestricted agent loops can bypass external rate limits or be manipulated into executing server-side request forgery. Every external integration, whether it's calling Stripe, querying Salesforce, or just fetching data from a weather API, becomes a target for exposing credentials. These memory and API vulnerabilities break the illusion of isolated user sessions, allowing a single attacker to systematically degrade the security posture of every future user on the platform. Let's review the comprehensive architectural map we've constructed. Watch this multi-stage path, from user input to agent manipulation, RAG poisoning, MCP execution, and data exfiltration. Notice what happens. Modern AI attacks are rarely single-shot prompt injections. Attackers bypass the central LLM to exploit surrounding connections. Secure an AI applications requires merging traditional cybersecurity disciplines, like locking down auth and preventing SSRF, with defenses against entirely novel, autonomous threats, like workflow hijacking and vector database poisoning. As these AI agents become increasingly autonomous, the sheer volume of external connections and the resulting attack surface will only expand. The organizations that successfully deploy AI at scale will not be the ones relying on purchasing the smartest foundational models. True AI security is achieved by building the most resilient surrounding architecture, rooted in strict access controls, component isolation, and immutable audit logs. Understanding how these systems are actually built is the only way to defend them.